Again, welcome to Data Structure and Algorithm, CS435 course. These lectures cover our course textbook, chapter 5, which is recursion. So our main objective is to learn about recursive definitions. Also, we are going to explore the base case and the general case of a recursive definition. Normally, a recursion or a recursive function consists of two statements, the base case and the general case. The base case will be the smaller unit of the problem. So we're also going to learn about recursive algorithm. How do we design it and also implement it? So first we start with the recursion definition. And here we say a recursion is a process of solving a problem by reducing it to the smaller version of itself. So normally in recursion or recursive function, we are going to have the base case. The base case will be the smaller version of the problem. And that's where, again, the problem will stop reducing itself. When you reach the smaller version of itself, it cannot be reduced no more. So we can see that recursion is more or less a concept of a loop. In a looping, we may do something over and over until a condition is false, then the loop will stop. In recursion, we may call the problem over and over by reducing it until it reaches its smallest version, then it will stop, return the final answer. Again, we're going to see an example soon. So a definition in which a problem is expressed in terms of a smaller version of itself is called a recursive. And also it has one or more base cases. So it depends on the problem. We may have a recursive function with only one base or may have more than one base. So a recursive algorithm is an algorithm that finds the solution to a given problem by reducing the problem to a smaller version of itself. And as we said, always a recursive may have one or more base cases, and that will be the smaller version of itself. So recursive method is a method that calls itself, and also a base case will be the case in recursive definition in which the solution is obtained directly. When we reach the base case, it stops the recursion. So the base case will be the smaller version of the problem. General solution, here we say we break problem into smaller version of itself. When we are solving problem in general, we can break a problem into smaller version of itself. Then the general case, in case in recursive definition in which a smaller version of itself is called, and it must eventually be reduced to the base case. When it reduced to the base case, again, that's when everything stops. The function cannot call itself no more. So a recursive method can have unlimited copy of itself. It depends on the problem. And also every recursive call has its own code, set of parameters, and also set of local variables. Now, after completing a recursive call, the control will go back to the calling environment. Also, the recursive call must execute completely before control goes back to the previous call. And again, we're going to see an example soon. Normally, the executions in the previous call begins from the point immediately following the recursive call. Now we have direct recursive, which a direct recursive means the method that calls itself. But indirect recursive means the method that calls another method and eventually results in original method call. So we have again direct recursive and also indirect recursive. Then also we have the tail recursive method. Normally the recursive method in which the last statement executed is the recursive call. Then infinity recursion, case where every recursive call results in another recursive call. So this concept here is like infinity loop. We know the base case will be the smaller version of the problem, and that's where the function will stop calling itself. It cannot be reduced no more. But infinitive recursion means the function will keep calling itself without stopping. So how do we design a recursive method? First, we need to understand the problem requirements. Recursion is a very, very detail-oriented, because in this recursive, instead of having a loop or using any method, here we are going to have the base case and also the general case, or we say the recursive case. The design of these two statements is very important. So we need to understand the problem requirement before we can even design. And also we need to determine the limiting condition, because this will give us the idea of the base case, the smaller version of the problem. So after we understand the problem requirement and we know the limitation of the problem, then we need to identify our base cases. Very important, because the base case is what will stop the function not to call itself no more. So we understand the problem, then we understand the smallest unit. Let's say, for example, they say we should find a factorial of a number. We know that a factorial of 5 will be 120. Why? Because it's 5 times 4 times 3 times 2 times 1. I will come up with the idea that, okay, since this function I have to call, I can use a loop, start the multiplication from 1 and I end at 5, or start from 5 and end at 1. So this means the smallest unit or smallest version of this problem is the factorial of 1. Okay, so if that is the case, we can come up with the idea of recursive method for solving this problem. Excuse me. By having the base case as the factorial of 1, or a factorial of 0 should be 1. Then factorial of any number will be the number decreased by 1. So factorial of 5 will be factorial of 5 will be 5 times factorial of 4. Factorial of 4 will be 4 times factorial of 3. So we reduce it all the way to 1, which will be the base case. So next, also we need to provide direct solution to each base case and also identify the general cases. Then we provide solution to general cases in terms of smaller version of the general cases. So now let's see an example. How do we find a factorial of a number? Now we know if I'm using a loop, I can, let's say I'm looking for a factorial of n. So I can go to a for loop and I'll start from 1. So my counter variable will be from 1. Then I'll say this loop will go up to less than or equal to n. I'm looking for a factorial of n. Then I'll increment by 1, because a factorial of a number will be, let's say factorial of 5 will be 5 times 4 times 3 times 2 times 1, or 1 times 2 times 3 times 4 times 5. So when I have this loop, I'll go inside the loop and I'll have a variable. Let's say the variable name is factorial. I will declare it outside the for loop, initialize it to 1, because it's going to multiply. If I initialize it to 0, my final answer will be 0, because 0 times any value is 0. So I'll initialize it to 1. Then I'll start from 1 times 1 is 1. We keep it. We increment the counter to 2. 1 times 2. We increment the counter to 3. 2 times 3, 6. We increment the counter to 4. 6 times 4. Then we keep going until our loop stop. The same concept we are doing here. That's this time we are not using loop, but we're using recursive method. So we know the base case will be a factorial of 0 will return 1. We are not doing a factorial of a negative value. We go up to 1 or 0. And the rule for finding a factorial of a number is a factorial of 0 is 1, a factorial of 1 also is 1. So that's our base case. Then our general case or recursive case will be the number times, we can see the function is calling itself fact, no minus 1. So if it's a factorial of 5, first we're going to get 5 times factorial 5 minus 1, which is 4. And we can see the function name the same. So this function will call itself until we reach when the number equal to 0, then we return 1, then we return the final answer. So again, this is finding a factorial of a number. We have our base case, which is if the num equal to 0, return 1. Then we have our general case, the function have to call itself until the num reach the base case condition. When the num becomes 0, we return the solution. So this is how we can trace the cause. So for example, here we are looking for a factorial of 4. So we can say beginning the num is 4. The function reduced by 1 to be factorial of 3. Again by 1, factorial of 2. By 1, factorial of 1. By 1, factorial of 0. Okay, if the num is 0, now the condition is true. If the num is 0, which is here, we return 1. So now we return 1 back. Then we get 1 times 1, because factorial of 1 is 1. So 1 times 1 is 1. Then we have factorial of 2. So we return 2 times 1, which is 2. Then factorial of 3 will be 3 times 2. We have 6. With 4, 4 times 6 is 24. So this function have to call itself reduce until we reach the base case condition. Then we return the solution. So another example here, this is to find the largest value in an array. We can also use the for loop for this. Actually, when we're going through array, we have the code for using the for loop to find the largest value in an array. But this time we are going to use recursive method. So to find the largest value in an array, our base case will be if there is only one value in the array, then that's the maximum value. Other than that, if we have more than one, then we have to keep comparing. So here we declare variable mass. This is our base case. We say if the lower index equal to the upper index, then we return the lower index. And this means we have lower index equal to upper index means at least have one item. If I have one item, the index will be 0. So it's only 1, the lower index will be 0, the highest index will be 0. So we return that item. If not, if that's not the case, then we are going to call the function to find the largest value. So to find the largest value, we say that if the first item, which now is called the least lower index, if it's greater than or equal to the mass, then we return the least lower index. The mass is the function that calls itself. We have the next value. Here we have the name of the array, lower index plus 1, so which means we move to the next value. Let's say lower index is 0, lower index plus 1 will be 1, next it will be 2, etc., until we reach the upper index. So this allows us to go through the items, the function will be calling itself, checking one item at a time. So when we get the first one item, then we come and check. Is the previous lower index greater than or equal to mass? If it's greater, then we keep it. So we still keep the lower index. If it's not greater, then we get a new mass, which will be this mass. Again, this mass here, the function calls itself by going through the items in the array. Lower index plus 1, next lower index plus 2, keep going. So again, that's the concept of, again, recursive function. So our base case is if we have only one item in the array. Again, base case is always the lower unit of the problem or the lower version of the problem. So if I'm finding the highest number in the list of array, the lowest unit of this problem will be if I have only one item. Then is the maximum, is the minimum. Another example is the recursive Fibonacci we know Fibonacci number means we had the two previous numbers. So for example, Fibonacci of 0 is 0 because I don't have any number in front, two previous number. Fibonacci of 1 also is 1. Then Fibonacci of 2 will be the two previous number. Fibonacci of 3 will be the previous two numbers we had. So that's the concept here. First, we have A, we have B. So we said that if n equal to 1, B is if n equal to 2. N means the number of items we have. Other than that, if we have more than 2 items, then we had the two previous values. So it will be, we call the function a and b n minus 1 plus a and b n minus 2. So we are adding, if I'm in the n position, n minus 1 means the previous value, n minus 2 means the two previous value. So we have addition here, we are adding the two previous value. This condition is only if n is greater than 2. If I have only one value, Fibonacci of 0 is 0. We don't have anything. Fibonacci of 1, there's nothing, there's no any two previous value, so it's the same value. So if it's only A, one value is B, return. Now, if it's 3, then I'm going to add the two previous value. So that's the design of the recursion. So the base case would be if n equal to 1 or 2, or we can use the A and B. If n is A or B, we return A or B. So let's see the concept here. So this is again Fibonacci recursion. We have A, B, and N. A is the previous value. B will be the next previous value. N will be the value we are looking for. So I'm looking for Fibonacci of 10. That's the 10th position. So as we said earlier, if we have only one item, then we return that item. A is the first item, B is the second item. So if n equal to 1, return A. Else if n equal to 2, return B. So those are our base case. As we said earlier, base case can be more than 1. Other than that, we had the two previous values. So this is the main key, and had n minus 1 plus n minus 2. And this function is called itself. So rfabno, that's the name of the method. So when do we use recursion and when do we use iteration? Example would be loops. Well, I would say that you can use either of them, the one you think is easy to implement or to design. We may have a problem. Using iteration will be difficult to implement or design. Or we may have another problem. Using recursion will be difficult. So always there's two ways to solve a particular problem, either by iteration or recursion. And here we say that iterative control structures use the looping to repeat a set of statements. Now, trade-off between the two options, sometimes recursive solution is easier. So if it's easy, best way. But the problem or disadvantage is that recursive solution is often slower because the function have to call itself over and over every iterate. But for loop, we just go through the list or the index of the loop. So recursive solution is often slower because it has a high overhead cost. Function call itself over and over. So we have another example here, which is a method to convert decimal number to binary. And we know in mathematics, if you want to convert decimal number to binary, what we do is that we divide the decimal number by 2. The 2 is the base of the binary. Then we keep the remainder. Binary numbers normally have only 0 and 1 digits, 0 and 1. So if you divide any number by 2, the remainder should be either 0 and 1. We keep the remainder, and later that remainder become the binary number. Now you divide all the way until you reach 1. So let's say, what's the binary number of decimal number 5? I will divide 5 by 2. The remainder is 1. I keep it. The answer is 2. Then I divide 2 by 2. The remainder is 0. I keep it. The answer is 1. When I reach 1, I can't divide no more. So I will add the last 1 into the remainder digit. Then I'll write it 101. So that means the decimal number 5, the binary number of it will be 101. So the same concept we are doing here. So this means since we cannot go we can't go less than 1. This is binary. Now, if it's octa, the base is 8, which means we can't go more than 7. So it will be 0, 1, 2, 3 up to 7. These are the digits that allow in octa. And when you count the digit from 0 to 7 is 8. That's why the base is 8. So how do we do this? Our base case is very straightforward. We know we can go up to 1. So our condition said if the number is greater than 0, which means at least up to 1, we are going to reduce it. So first, as we saw the algorithm, first we have to divide the number by the base, then we keep the remainder. So here we call the function. This is recursion. The function name is decimal to binary. That's the name of the function. So we call this function by dividing the number by the base. Then when we divide the number by the base, we need the remainder. So what do? We print out the remainder. System.out.print num modulus base. So we print out the remainder. Now, when we print out the remainder, if the answer is not yet 1 or greater than 0, then we say keep going. We divide the next value like as we did. We start with 5. 5 divided by 2, the answer is 1. The answer is 2, remainder 1. Since 2 is greater than 0, we are going to divide again 2 by the base 2, which is again 0. The answer is 1. So when we get the answer, we can see that the remainder, we print it out because that's our solution we want. Then next we check. And if this condition is true, we are going to divide and the remainder. So we'll have 1. Is 1 greater than 0? Yes. But when we divide 1 by the base 2, the answer is 0, remainder 1. So we print it. Now, is 0 greater than 0? No, so we stop there. So we print our 101. So again, this is the whole concept of binary number converting to decimal or decimal converted to binary. We can use recursion. So this is the tracing. So we have, in this case, we want to convert 13 to a binary number. So the base is 2 because it's binary number. The number is 13. The condition said is the number greater than 0. Yes. So we divide 13 by 2. The answer we get will be 6. The base is still 2. But we have remainder 1. So we have the output. We have the system.out.print to print the remainder. So we print the 1. Then next, we divide 6 by 2. The answer will give us 3. So we have 3 next. And then 6 modulus 2, the remainder is 0. So we print 1 and 0 now. So next will be 0. Then the same thing, we have now the norm is 3. Yeah, norm is 3 is greater than 0. So we divide 3 by 2. The answer will be 1. And also remainder 1. So now we have 1 and 2. Is 1 greater than 0? Yes. So let's divide 1 divided by 2. The answer will be 0. The remainder also is 1. Now, is 0 greater than 0? No. So we stop there. Then we return the answers. So the decimal number of 13 to convert it to binary, we get 1, 1, 0, and 1. So again, this will be the conclusion of recursion function. And again, the homework assignment has been posted in the week 5 folder. And if you have any question about the assignment, please feel free to send an email. Thank you and wish you the best.